Good morning, friends. Today we are going to start the unit 3 of the paper 2 of the physics. In that we have to talk about the first topic is the origin of the quantum theory. We have to first of all talk about the quantum mechanics. Quantum mechanics in German was coined by a group of physicists including Max Born, Werner Heisenberg and Wolfgang Pauli at University of Göttingen in early 1920 and first used by the Bonds in his research paper Zur quantum mechanics in 1920. The classical mechanics based on the Newtonian formalization. Classical mechanics explains the circular motion of the object which are directly observable or observable with the help of the instrument like microscope. In addition to this motion of the charged particle in electromagnetic vibration in the string, elastic collision in solid, molecular motion of gases, optical phenomena such as a refraction, diffraction, scattering, dispersion, polarization, etc. could be explained with the help of the classical concepts. Some phenomena were discovered in the beginning of the 20th century, such as the black body radiation, photoelectric Compton effect, atomic spectrum, specific heat of solid at lower temperature, etc., could not be explained by the classical mechanics. Therefore, new concept was propounded to explain this phenomena led to new mechanics called quantum mechanics. This makes Planck, Einstein, Bohr, then the de Broglie, Max Born, then the Paul Dirac, Werner Heisenberg, Pauli, then the Schrödinger, Feynman all contributed in development of the quantum mechanics. In the 1901, Planck introduced the quantum concept that eventually led to conclusion that the radiation is not emitted in continuous fashion but in discrete bundles of the energy each equal to h nu called quantum photons. Small packet of energy is called as a quantum or a quantum say photon. This new idea introduced by the Planck was too revolutionary in the development of the quantum mechanics. Einstein in 1905 applied his quantum concept of the radiation to explain the photoelectric effect which could not be solved using classical theory. In 1907, Einstein successfully explained the problem of specific heat. In 1930, Bohr used these ideas for the condition to explain the original spectrum lines. In 1902, Compton applied these quantum ideas to phenomena of the scattering of the X-rays. De Broglie put forward theory of the matter waves, stating that the particles can exhibit wave characteristics and vice versa. Building on de Broglie's approach, modern quantum mechanics was developed in 1925 when the Werner Heisenberg, Max Born and Jordan developed mechanics and Schrödinger invented wave mechanics. In 1927, Heisenberg formulated uncertainty principle. Paul Dirac in the same year began the process of unifying quantum mechanics with special relativity by proposing the Dirac equation for the electron. He also pioneered the use of the operator theory, including the infinitional bracket notation. During 1940s, the formulation of quantum electrodynamics made by R.P. Feynman, Dyson, Schwinger, and Tomonaga, which describes the quantum theory of electrons, positron, and the electromagnetic field. In 1975, the theory of quantum chromodynamics was formulated by the Politzer, Gross, and Wilczek. Squinger, Higgs, and Goldstone, the physicists Glasgow, Wensberg, and Salam independently show how the weak nuclear forces and the quantum electrodynamics could be merged into a single electroweak forces. So in 1917, this particular scientist Glasgow, Salam, and Weisberg were awarded Nobel Prize for their contribution. Now we have to talk about the black body. Black body will nothing but such a body where the radiation falling on that body is partly reflected, some of it is absorbed and rest is transmitted. Therefore, we have R plus A plus T is equal to 1. Where A is the coefficient of absorption, R is coefficient of reflection, T is coefficient of transmission. A body which absorbs all wavelength incident on it is called as a black body. That may come for the MCQ. In practice, no material has been found to absorb all incoming radiation. Lamp black and platinum black are the practical black body as they absorb about 98% radiation which incident on it. For the perfectly black body, equation 5.1 becomes A is equal to 1 as R is equal to T is equal to 0. Thus, a black body absorbs all the wavelength that fall in it in all temperatures. A black body not only completely absorbs all the radiation falling on it but conversely behaves as a perfectly radiator when heated. Black body spectrum is shown here. A particular temperature, the black body emits the maximum of energy possible for the temperature. These radiation emitted are known as the black body radiation. This black body spectrum, which is the continuous spectrum at a particular constant level, the intensity of the radiation emitted by the black body is not uniformly distributed over the whole range of the wavelengths in the continuous spectrum. The intensity of radiation increases with wavelength of the radiation. At particular wavelength, the intensity becomes maximum, and beyond that, the intensity decreases gradually. As the temperature of body is increased, the peak wavelength shifts toward the smaller value. This result can be easily observed when the blackened platinum wire is electrically heated. It becomes dull red at 500 degrees centigrade, cherry red at 900, orange red at 1100, yellow at 1250 degrees centigrade, and finally white at 1600 degrees centigrade. This indicates that the temperature rises, the radiation emitters contain more and more shorter wavelength. When displacement law, as the temperature of the black body is raised, it observed that a maximum intensity of emission shift towards the shorter wavelength side. When the principle of thermodynamics applied to the black body radiation, the relation obtained lambda 0 t is equal to constant. The value of the constant called Wein's constant, that is equal to 2.898 into 10 raised to minus 3 millikelvin. Wein's displacement law states that as the temperature of the black body is raised, the maximum intensity of radiation emitted is displaced towards the shorter wavelength side. That you have to remember. The next part we will see in the next lecture. Here we will stop. Thank you.